question? If not, no, I don't see any other question. Then thank you very much for your talk. And now I let Naftali to start his talk. Thank you.
Hi, good afternoon. Do you hear me?
Yes. Yeah.
Okay, good. You see my screen.
Yeah.
This is going to be a much more speculative and theoretical presentation. And the ideas that I'm going to describe are not even closely as worked up as what Joshua just told us, but he actually presented most of the issues about biological learning and biological background. What are the problems with gradients? So I actually want to share with you some interesting insights and algorithms that come from the understanding of deep learning, at least, as some sort of an information optimization problem. I know this is not generally accepted and certainly not the only way of thinking about deep learning, but in my world, we are thinking that there are essentially only two macroscopic functions that really characterize the learning in large scale, when you can use typicality arguments. So essentially, this is an asymptotic theory, and this is what we call the information bottleneck framework. And essentially, it tells us that the layers of deep learning converge to some interesting line in this two dimensions: information about the input, information about the label, and this if the rule is even slightly stochastic. I mean, I need this stochasticity for regularity of the problem because you don't want to take logarithms of probabilities that are 0 or 1. This somehow is a singular case, but it's not really a major issue. The limit of deterministic rules is very well defined. So essentially, the basic insight that we gained over the years is that you can think about what happens in stochastic gradient descent as some sort of pushing the layers one by one to this optimal line. And this is what, and since they form a Markov chain of representation, they form what in information theory is called a successfully refinable code. And I'll describe this in a second. Not only that, there is some very strong condition for this to happen, which means that the map from the input to the layer, which I call the encoder, and the map from the layer to the label, which I call the decoder of the layer, must obey some sort of self-consistent equations, which I'll describe in a second. So this, I'm going to use this plus the assumption or the fact that in a feed-forward neural network, at least, the layers form a Markov chain in the sense that I can calculate one layer from the previous one and only that. So they form a Markov chain in a mathematical sense. And I'm going to use these two facts in order to look for what we call local learning rules, which are not yet biologically plausible, but in that direction, where essentially all the gradients information are not back propagated or in any way, but can be calculated locally for every one of the layers. So there are no chain rules involved. And I'm going to show you that it's actually very simple to take the self-consistent conditions on the encoder and the decoder of the layers and turn them into local learning rules. So you can call it information bottleneck without chain rules or without backpropagation, but it's actually, I believe that it carries a much more general message to biology, and I may say something about it. And then I'm going to discuss the stability of this algorithm and the convergence time, which we can also do relatively easily. And what turns out that this algorithm converges very fast, except in some very special points, which we call the critical points along the information bottleneck, where essentially the topology of the representation change. And this actually suggests some interesting interpretation from the hierarchies also in biology, where essentially you want your representation to really capture those topological transitions of the input. And I'll describe this. And then I'll talk a little bit about algorithms. In particular, in order for this to work, we need some sort of, we can't do it non-parametrically in general in high dimensions. So we need some sort of parametric assumptions about those encoder and decoder. And the most common one are to assume Gaussian and linear maps. This is the easiest one. This is actually analytically tractable completely. And there is a generalization of it, which is the Hilbert-Schmidt information criteria, which is essentially composition, which is essentially a kernelizing the network and then work in the kernel space. And then it looks very much like Gaussian, but in this kernelized space, like every other kernel method. This have been tried and suggested by other people, and they actually show that this idea works pretty well even on large-scale problems. So just reviewing the basic idea of the information theoretic approach to deep learning, we're actually thinking about a layer and layered neural network as a cascade of representation transformations, layer by layer. I mean, actually, you can even make it in time if you really want to. It makes it a lot more complicated because neurons can share different layers, but in principle, it works also if you think about recurrent neural networks. But then the question I'm asking, or the two quantities I'm interested in, is essentially how much information about the label is transformed or sustained or maintained in every one of those hidden layers when you train the network to optimally classify something. So that's an old picture. So we're actually interested in the internal representations layer by layer and in the information about the input that flows through the network. And in order to quantify these things, theoretically at least, we use the famous information theoretic quantities. I just want to remind all of you that I'm using two functions here. Essentially, one is the KL divergence of two distributions, which I'm sure all of you are familiar with, the D of P and Q. And the second one is the mutual information, which essentially is the KL between the joint and the product of the marginals. And this essentially tells me it's a measure of independence, but it's much more than that because it obeys this data processing inequality. So essentially, if I move along a Markov chain like in these neural networks, I mean, each layer can be computed only from the previous one, then mutual information, both about the input and about the label, must decrease. This is what we call data processing inequality. So these are the fundamental quantities I need all of you to remember. Of course, if there is no loss of information, so if there's both X and Y goes through some sort of a invariant, a one-to-one transformation, the information is not lost, it's preserved. Of course, this is why many people are confused about it, because mutual information in general is very hard to estimate in high dimension. And in order to make sense of it, you need some sort of quantization or discretization or some noise. And this is a crucial point, which I'm not going to elaborate here, but we know now that essentially we need to use the right measures of information, which are related to the actual quantization or actual noise level in each one of those layers. So essentially, just using DPI, we know that there are those chains of inequalities. Information can only go down about the input X and can only go down also about the label Y, because the label Y is to the left of this chain, essentially. And what the network is generating is some sort of prediction of the label, which I call Y hat, which is very different from Y. Of course, if the network is well trained, this Y hat is similar to Y, but it's not the same. Of course, in between, I assume that information is going to be lost. It doesn't have to be lost. I mean, we know that ResNets and other RevNets and other kind of networks don't necessarily lose information, but I argue that for the decoder to actually be efficient and generalize well, it doesn't have to use all the information in the layer. So essentially, I'm talking about what is the minimum information required in each one of the layers in order to actually achieve good generalization. And again, I don't want at this point to get into all the arguments about whether compression is necessary or needed for generalization. This is an open question, and I have a lot to say about it, but not right now. So essentially, we think about data representation in general as made out of two phases. One of them is what we call the training, which is the map from X to some internal representation, which I call here X hat, and later I call T or H. And during the training, we use the Markov chain Y, X, X hat, which is essentially telling me generate a good representation of X hat, which contain as much as possible information about the label Y. And then in the application on the prediction phase of the network or any machine learning, actually, we use the Markov chain X, X hat, Y hat, essentially tells me, I give you only X, I don't give you Y. you need some sort of representation in X set, which gives you a good prediction of Y hat. And we recently actually suggested a general way of improving this prediction, which we call the dual information bottleneck, but I'm not going to talk about it here. Just mention it briefly because it's actually related to this biological representation, biological learning. So again, the story, as many of you know, each layer is now characterized by these two functions. The encoder, which is in general a stochastic map from the input layer to the layer, which I call PT given X, so the encoder of the layer, and the decoder, which is the map from the layer to the label. And in order for this to make sense, I actually argue that only these two numbers, the mutual information between the input and the layer, and the mutual information between the layer and the label, actually tell you most of what you're interested in terms of sample complexity and in terms of generalization. And this is something I've been saying for many years. People just don't believe it, but I still stand behind it. Now, when we talk about local representations, what I mean by that is that instead of using the full encoder, I'm actually using only 3 consecutive layers. Let's call them TI-1, TI, and TI+1. And I'm going to call it a local learning rule, which in this talk is assumed to be more biologically plausible. It's not fully biologically plausible than the full backprop. So you can think about it, as I said, information bottleneck without chain rules and of derivatives. And essentially, then what I call the local encoder is the map from the previous layer to my current layer, and the local decoder is the map from my current layer to the next layer. And of course, the whole idea is that this is done in parallel or consecutively somehow along the network, or almost independently, given some fixed input and some forced label, which are forward and backward propagated, but I'm not propagating gradients, I'm propagating the map itself. So there's no, this is what I call the successively refinable or successively refinable code. And again, if this actually happens, there are some mathematical conditions which I'm not going to get to, that the KL, the distortion in the prediction of the label is actually made out of sum over all these triplets along the network. You can think about it also in terms of simplicism, and I'm talking about distribution. Each one of those layers is some sort of a clustering of your data points in the simplex of the label, of the distribution of the label, and the simplex of the distribution of the input. And again, this is one way of thinking about the whole bottleneck in a slightly more geometrical way. So the main message we've been saying for a few years now is that when you look at backprop or its stochastic gradient descent, actually many other gradient methods, not necessarily SGD in the plain vanilla form, with some sort of a batch, which is, so the noise actually helps me here. The layers are moving from such, so there's this data processing inequality. You see that information, somehow you don't see my cursor, I don't know why, but imagine that I'm pointing on this lower curve. So this actually is the initial conditions of the training, and what happens during backpropagation is that all the layers start to climb up, obeying DPI, data processing inequality, of course, all the way. And then at some point, the layers start to move slower towards this optimal line, which is the minimal information that I need to remember about the input, subject to some constraint on the label. This is what we call for many years the information bottleneck limit. Now, the interesting point is that the layers converge to different locations on this line. So they lose different amounts of information from point to point. So now and of course there are all sorts of finite sample issue. What happens if you have a small sample? Then the curves look very different. I mean, they converge to a suboptimal curve, and the more samples you have, the higher this curve, which is also some sort of information bottleneck limit of a much noisier distribution. What is really interesting, and that's all like empirical evidence that we've been showing for some years now, is that even when you change the sample size, the layer seems to follow the intermediate layer, some sort of trace, very interesting traces in this plan. This is what we call the information plan, the information about input versus information about the label. So there's some very consistent way in which those layers converge, even when you train, you increase the sample. And then eventually they glide or slide on this asymptotic line at the end, which is which is slightly curved because of the stochasticity of the noise. And each point on this line is completely characterized by what we call the temperature. I'm going to skip some of those theoretical things. You can read it, but you can think about the whole thing, this minimization problem. What determined this line is this problem that we call the information bottleneck bound. Essentially, okay, if they all converge to such a line, this line can be analytically or numerically computed just by solving this optimization problem. Minimize the information about the label, about the input, subject to a constraint with some Lagrange multiplier beta on the information about the output. And what is nice about it, and that this is completely solved by this not close, it's not explicit because it's a self-consistent type of equation. You can think about it as clustering with the KL divergence as a distortion measure. Essentially, you can think also about it as some sort of iterations, which we sometimes call the Darimoto-Blaut or the Blaut-Darimoto iterations in information theory, between the encoder and the decoder. And this converged pretty fast, I mean, exponentially fast in many cases to this equilibrium. It's very much like EM, but of course it can have very problems with convergence. So essentially this line on the right, again, you don't see my cursor for some reason, but this black line is the collection of all the solutions of this variational problem when I move beta. And beta is essentially 1 over the slope of this line. So higher beta means I don't lose any information, and smaller beta means I'm allowing to lose some information. And the claim is that deep neural network, the layers of deep neural networks actually achieve this line. So this is an assumption I'm going to make here. Now I want to localize this algorithm. Okay, I'm going to skip the finite sample and why compression is actually essential, theoretically at least. And when I say compression, I mean, it's not that there is no information in the layer, but I don't need this information in order to make the prediction. So the decoder, it's really the sample complexity of the decoder, not the encoder. And if I'm optimal, so the layers are going to lie somewhere along this black line. And in general, there are 2 types of losses, the compression loss, which is how much you lose because you force compression, and the finite sample loss, which is how much you lost because you have a noisy version of your distribution. And it's the sum of these 2 losses that I want to minimize. And this is what gives me this trade-off. I have to be somewhere in the middle. Otherwise, if I'm using too complex representation, I'm going to overfit. I'm going to have a lot of unnecessary information in my representation. So that's, again, this is the general theory of the information bottleneck in general. We also know that empirically, when we look at some real problems, and actually many problems, we see that the layers actually converge to this theoretical limit. Here you see, if you look at the axis, I'm talking about very high information. It's a one bit classifier, a binary classifier. So it's really the top 2% of this line where you see this curvature, and you see that different layers converge to different values of beta, which means that each layer is actually remembering less and less information. And the last one is really remembering essentially 1 bit, which is just what they need in order to make the label prediction. Okay, so I hope that this is clear, and it's not new. And of course, if there is this, what we call successive refinement, essentially the distortion of the last layer is the sum of this accumulated loss of information layer by layer. So I have this approximate equation, the distortion between the prediction of the label from the input itself and the prediction of the label from the last layer is just approximately a very good approximation, a sum of those intermediate distortion layer by layer. So that's very nice because I can actually use this in order to get my local information bottleneck rules. So this is the new part. I never presented it before. So essentially, you take the encoder and decoder equations, which we have in the information model. So one of them tells me is that the optimal encoder of a layer T is exponential in the KL divergence between the prediction of the label from the data itself and the prediction of the label from the layer. And so this is a very simple Gibbs-like distribution, which has a very nice, and beta has this interpretation of a resolution or inverse temperature, if you want. Now, what we do is we take local perturbation of the encoder and the decoder and essentially take the derivative or the variation of this log and of the log encoder and log decoder. And what is nice is because the log takes the the KL from the exponent, is that you get a very simple linear relationship. The variation of the log encoder is a linear average over the data, essentially, over the training data, in this case, only the label, given X, of the variations in the log decoder. That's very easy to derive just from taking the derivative of the first equation. And now I'm actually going to use the Markov condition, which means that the probability, both probabilities, X given T and Y given T, are products of all those intermediate layers. So I'm using very explicitly the Markov condition for the feed-forward deep neural network. I assume that there are many layers that makes things easier. So T0 is X and Tk is Y, and in between I get this product. So one of them is a product of all the encoder layers, and the other one is the product of all the decoder layers. Now I take the derivatives with this, of the variation of the encoder and the decoder with respect to the parameters of one particular layer, of the weights prior, the incoming weights for each layer, and then the weights of the outgoing weights, the fan in and fan out of each layer. And what you see is that this decoder equation, there's an approximation here, which is due to the fact that I'm ignoring the interaction between different representation. It's a very small correction, turns out to be in practice. So essentially, the local derivatives of only one layer between the incoming and the outgoing weights are linearly related in a very nice way. And notice that what I have in the sum, what I average of is just the map of the input to the previous layer and the map of the label to the next layer. And that's all I need to do, average over this with respect to the data. So essentially, I don't need explicitly to have this conditional black distribution. Now, this is what I call a local learning rule, because the gradients are all local. They're not propagated from anything. And all I need is just to hold the input and output somehow, and maybe use Bencher's nice algorithm to propagate the image itself without gradients. Now, this I call biologically plausible. Of course, we can argue about it. Notice that beta here is a parameter, which essentially is a resolution parameter, which is going to tell me what is this trade-off between compressing and predicting. And it's going to tell me essentially where is this layer going to converge on the curve. Okay, and then you can do exactly the same thing to the decoder equation. And the decoder equation is just a Bayes rule, or just a chain rule of probabilities. But now if you take variations, it's very simple. The delta P is a linear combination. Delta P in is the linear combination of delta P out. But then you need the logs. I need the logs, by the way, in order to break this factorization of the Markov into sum. And then when I take derivative, all the other terms disappear. So we really need the log. So the log makes it a little more complicated. But you know how to take derivatives of logs. And essentially, you get, again, a very similar backward connection, which connects the derivatives of the decoder to the derivatives of the encoder through some sort of averaging. And I argue that this averaging can be done explicitly by simply running through the training data. Now, there is this tricky term in the middle, the back or the inverse encoder and the inverse decoder, and which you need to play a little bit with in order to work with it, because this is not explicitly available to you. So you use Bayes rule and again use we estimate this ratio of Px given T to Py given T. This is somewhat a tricky part in this story, but let's leave it like this now. Okay, so essentially what I showed you is that up to this minor approximation, you can localize the information bottleneck equations completely to one layer. So that's very nice. And the question is, how do we actually solve it? So we have these two equations. The derivative of the encoder are related to the derivative of the decoder. Respect, and theta here is what used to be W before. It's the local weights or the local parameters. And of course, this in general, this non-parametric way of thinking about it is not practical. I mean, this is not something you can do in high dimension. So what we need to do is to work with some sort of parametric forms. And of course, what people are doing is either assuming linear Gaussian, which essentially, but notice that this actually works beautifully for all the standard nonlinearity in neural network, like sigmoids or ReLUs or whatever, because then you have a very simple parametric form, essentially. It's a matrix, it's a matrix product plus some nonlinearity, which I can easily derive. But actually what I prefer is to work with what we call exponential forms, which essentially assuming that this mapping from layer to layer is a function of just a certain collection of function, which I call here AR of t, which can be the first, the linear function and the quadratic function, and whatever moments you actually care about in terms of the representation of tj, plus some coefficients which depend on these parameters. So essentially, I want to optimize, and this is again something we actually do in the dual information bottleneck paper, which is just submitted to NIPS, but it's around, you can find it. And of course, the easiest way is to take A's to be just linear and quadratic, and then you get a Gaussian, essentially the log, if the log is linear or quadratic, the map is Gaussian, and then these equations that you see on top become very simple. They're essentially just linear CCA, canonical correlation analysis projection of one layer with respect to the next one, and so on. So this is classical Gaussian information bottleneck, which we know for 15 years now, but it just boils up again, but you do it between three consecutive layers. So the middle layer is going to be a projection of the previous one, which preserve all the correlation or the information, the linear information in this case, about the next one. And there is a very nice extension of this Gaussian picture, which is, as I said, called the Hilbert kernel information composition, which is actually a very nice idea, which was used actually independently. I didn't know about these people in Australia or New Zealand that wrote last year a nice paper which does exactly what we suggest here. They don't, not with all this mathematics, but they use this HKIC essentially to Gaussianize using kernels the map between linear, and then they actually wrote a paper about information bottleneck deep learning without backpropagation, which seems exactly what we are suggesting, or I'm suggesting here for some time. Okay. What is really interesting is to look at these gradients. I mean, again, that's something which most people don't really do. So if you actually look at the log of the error, the probability of the label given the input at a certain layer, and look at the SVD of this, at the singular value decomposition of this, you can actually see this very nice picture. So essentially, we know how these gradients behave layer by layer. So this is a little bit busy slide. Let me try to explain it. So essentially, this is MNIST. So we have classes of digits, and in this case, there are only 4 of them. So it's a subset of MNIST. And what you see in these projections is essentially how the gradients look after training in these 2 planes of one layer and the other lane, according to the first 2 singular values in this case, singular vectors. Now, what is really nice and very clearly seen here is that each cluster finds its own arrow, its own direction in this subspace. So there's a very nice separation. The gradients in each between these two classes look very different. They point in very different directions. And what you see that if you move from one layer to a deeper layer, the dimensionality goes down, which is essentially a manifestation of this compression or loss of information. And you can also see this in the singular values between those 2 layers. But what is really nice is that when you go deeper, this gradient picture becomes a lot cleaner. It means it's not just loss of information, it's exactly loss of the irrelevant information and preserving this relevant one. Now we see exactly the same type of pictures of gradients when we look at this local learning groups. They're almost the same as if you use the global learning groups, which means that the local information bottleneck indeed achieves almost the global optimum. Now I just want to say a few words. I know I'm almost out of time. I still have a few minutes. So essentially, the stability question is a very interesting question. So how do I know that this algorithm actually converge? So essentially, again, we have the information bottleneck equations for us. And essentially, I can take this variation of the encoder and decoder and plug them one into each other, and then you get essentially an eigenvalue problem. It's a nonlinear eigenvalue problem. And it tells you, and as long as the eigenvalues of this matrix C, which is the composition of all these terms that I mentioned before, together, as long as the eigenvalues are inside the unit sphere, I know that I'm converging, and I'm converging exponentially fast. But there are very interesting points where these values cross the boundary, which means this is what we call the critical point. So we actually know that there are very special values of beta where this algorithm is not going to converge, it's going to diverge. But these points are very interesting topologically. It's precisely those peaks that you see on the lower line here is the convergence, the number of iterations, and you see that they diverge exactly those critical points. So this raises an interesting suggestion that maybe we need our layers to, they are going to get stuck there. The phenomenon that we call critical slowing down, essentially near these points, the algorithm is going to be very sluggish. And the question is whether we like it biologically or hate it biologically. The question is, why do we need these critical points at all? Okay, so these critical points are really some sort of second order phase transitions. I don't want to say too much about it. I just want to say that we actually know very well how to analyze the stability of this algorithm and how to analyze this, slowing down and relate it to topological changes in the representation. And in general, just to give you a slight picture of what's going on here, a very general rule will have this very convoluted, very complicated picture of bifurcations of the representations, and what I know is that I want to stay away, actually not too close to those splits, which are essentially some sort of cluster splits in clustering. And that's where my algorithms, this local algorithm is not going to converge. Whether it has any biological implication, I don't know. I have all sorts of guesses and speculations, but it's an interesting phenomenon. All right, I just want to summarize. So the deep learning layers from these optimal bottleneck successive codes, and they're optimal in the sense of generalization wise, if under some assumptions that we actually have to clarify. But and in this case, the encoder and decoder of each layer obey these IB equations, and we can localize the IB equations in the case that we have a Markov chain that enable this local decomposition of the information bottleneck. And they converge exponentially except at critical points of the information bottleneck, which means splits of the topology of the representations. There's actually a lot to say about invariances and symmetries, because those which are actually related to Tommy's talk, but maybe for the discussion later. And the local equation is simple for Gaussian, for linear assumptions, and can be kernelized. And this was actually done by these guys in New Zealand, I think. So we actually have some sort of an empirical evidence that whole ideas work. Thank you very much.
Thank you very much, Tali. So I see that both Christina and Joshua, they have many questions. Since we are running out of time, I ask both of them to open the microphone and to ask just one question to you, okay?
I didn't see them, but okay.
Christina?
No, I have to.
I think we're just having a separate conversation somehow. So I think a fundamental question is how does the only way that internal representations relate to the data is transitionally. So you sort of, we have a whole bunch of layers that get learned by self-consistency rules. And the only way these internal representations get tied to the data is at the very extreme, so at the ends. But
yeah, sure.
My intuition is, yes. Yeah. So my intuition is that the more layers you have, the harder it's going to be to do the tying to the data again. So I was wondering about convergence properties with respect to the depth of the network. If you have some intuitions about that.
So this local algorithm doesn't know about other layers in principle. I mean, it's all local, yeah. But the only thing you need is to project somehow the input to the first, the previous layer and the output to the next layer and hold it there, because I need to average over those in terms of, so there's a mechanism which I don't even have any clue how to do it biologically, but at least all I know is that I need to project the input and project the output and eventually iterate those encoder, decoder. And I know that in general it's converging very fast, so just a few iterations, 5, 6, 10 iterations are enough now. There are all sorts of dimensionality issues which I raised after Joshua's talk, of course, because I have, I assume that I have the gradient respect to the whole layer, but this can be impossible to calculate biologically, but that's why we have other tricks to play with. But in principle, this is completely local. Each triplets of layers is doing its own equilibration or a self-consistent encoder-decoder composition. And what we have proved mathematically is that this local optimization is going to converge to the global optimum line under the usual assumption. These are all non-complex problems.
So yes, but these local optimizations need to converge to the global optimum. So the alignment between I still think the convergence speed should depend on the number of layers, because you still need to have a diffusion of the information across the entire hierarchy to some degree.
Sure. But this is a slow process. I mean, I project an input to the previous layer, project the output, and then hold it there. So there's some sort of assumption that I can do this self-equilibration of the encoder and the decoder without changing the input and output. And then I change the input and output and do it again in batches or whatever. There are many synchrony or not synchronous or non-synchronous, by the way. It can be done in each layers. So we haven't tried it non-synchronously. We do it layer by layer, but I guess it can be done non-synchronously. The whole thing is quite robust, but there's a lot more to explore here.
So I just want to add something about the backward process. So going from Y to Ti plus 1, right?
Yeah, right.
Well, you didn't explain how you do that, but I think there's a fundamental issue here, which is if you do that in a way that doesn't take into account X, I don't think this is going to work.
My assumption is that X and its label in the training data are somehow imposed on the beginning and the end of the network together.
So what I mean is that for a given, if you only use Y to find Ti plus 1, and you don't use X, or Ti minus 1, then there's so many possible Ti plus 1s that are consistent with Y, but are so far away from what the local encoder decoder is supposed to do. That it can achieve in a small change, right? The problem is you're only going to be allowed to do a small change of this local encoder decoder layer. And if you only allowed a small change, you should take into account, what is realizable by a small change depends on the current value of Ti minus 1 and not just on Y.
Sure. So first of all, there are many, in general, a continuous manifold of optimal solutions. We know that. I don't have to converge to your next solution. I know I don't. So in some sense, you converge locally. Somehow, my assumption is that you somehow got close to the optimal line, because only there I can actually use this particular algorithm for final convergence. So there are many underlying assumptions. At the beginning, something fast happens, which is a very crude type of learning. I don't know how to do it. But once you're close enough in the vicinity of the optimum, then this alternating encoder-decoder, it can be done asynchronously for every 3 layers, as long as I can keep the input and output there for a while. I don't claim that I know how to do it biologically. But actually, after hearing your talk, I think maybe you can combine these ideas somehow.
Okay, thank you very much.